First lecture from Konstantin Zarembo, please.
Yes, I'll talk about integrability in AdS CFT. And by AdS CFT, I will mean the simplest example where we have a duality between n=4 superangular theory in 4 dimensions and string theory in AdS 5 x S5. So on the one hand, we have n=4 Superang-Mills theory. And this is quite remarkably equivalent to type 2B strings on AdS 5 x S5. So is everything visible on the back rows? So if not, please let me know if I'm writing too small letters. This is essentially one and the same theory, and it is parameterized by one continuous coupling, which is Young-Mills coupling, or more convenient parameter is the 't Hooft coupling. And a discrete parameter of the gauge group, which will be take to be SUN. So on the string side, apparently there are 2 parameters. One is the string tension and the other is string coupling, and they're related to the 't Hooft coupling and N in the following way. So the simplest limit, and the one that the only one I will discuss, is when we take n to infinity. This is known as the planar limit. In gauge theory, while fixing the 't Hooft coupling, and in string theory that can be seen to correspond to string coupling going to 0. So in that limit, strings are free. So it's no quantum gravity. So it seems to be a very simple limit, but it is not, because the string tension remains finite. And basically, the string description is simple when we take this string tension to be large. So then the string is very rigid, or has a short length, because otherwise it's penalized by the large tension. And so the description is either in terms of classical supergravity or classical gravity, if you wish, or rigid strings that basically follow geodesic, minimize the length. Whereas the gauge theory has a simple description where when the 't Hooft coupling is small, then we can use usual perturbative diagrammatic compute analysis, or compute Feynman diagrams, or the biorder. And then in principle, there is an interpolation between these 2 regimes, which is terra incognita. That's complicated. So both descriptions become equally complicated. And integrability is the way to understand how this interpolation works. So although right now the methods of integrability mature to the degree that you can really do computations at finite coupling, I will mostly talk about perturbative gauge theory, just to introduce the structures and concepts that arise and that are useful, that can be extended to the finite coupling. All right, so the reason why this system is integrable is actually geometric. It has to do with the fact that AdS 5 x S5 is a very symmetric manifold, so a round sphere, and the AdS is also it's a complex continuation of a round sphere in essence. And for such symmetric manifolds, if you embed a string worldsheet in them and follow its evolution in time, its evolution is described by integrable equations. Or if you fix a gauge on the worldsheet and consider a string which can fluctuate, the fluctuations of the string are described by 1+1 dimensional quantum field theory, which, in addition to obvious conservation laws, contains an infinite hierarchy of conserved charges, and that's what makes it integrable. So if you consider string excitations, they carry momentum and energy, but also it turns out that in addition, there is an infinite number of conservation laws, and this is what defines an integrable system. So a consequence of existence of this extra conservation laws is that only there is no particle production in two-dimensional theory. So if you collide two particles, they will never produce four particles in the out state. And moreover, they will the only thing that can happen in their scattering is that they can exchange momenta. So in 2x2 scattering, by the way, this follows from two-dimensional kinematics. There is integrability is not important here. But if you add infinite number of conservation laws, then any scattering that can happen is 2x2. So the only quantities that you need to know about this theory is the dispersion relation of its excitations and a 2x2 scattering S matrix. And those two can be reconstructed by symmetry. So in principle, I could have started with just telling you how to compute epsilon of p and the S matrix of p. But then you need to know what to do with them, how to extract, say, the spectrum of a theory, how to connect them to Feynman diagrams, and so on. And that's probably the most interesting part of the story. But it's kind of difficult to explain it that way. And so I will go in the opposite direction. Namely, I'll start with perturbation theory and just demonstrate that that if you want to organize it in a nice way, then these integrability structures arise and really help in computing perturbative quantities. But behind that picture, you need to understand that there is always a non-perturbative structure that extends to arbitrary couplings. So the first thing I need to define then is what field theory we are dealing with. So I'll start with writing down the Lagrangian of n equal 4 super Mills. So, as you have learned from previous lectures, N=4 superrank Mills is secretly 10-dimensional theory, right? So it lives on the brain that is embedded in 10-dimensional space. So the interactions or particles can propagate only on this brain. But then there are extra dimensions that complement it to 10 dimensions. So if you denote coordinates on the brain by x0, x1, x2, x3, there are also coordinates x4 to x9. And, well, these coordinates exist, but they do not exist in the following sense, that the fields themselves, which are vectors, spinors, and scalars, they have Lorentz indices as if they live in 10 dimensions. So for instance, the gauge field on the brain would actually have 10 vector indices. So it will be a full 10-dimensional vector, but it will depend only on 4 spatial coordinates along the brain. So M runs from 0 to 9, and X mu has indices from 0 to 3 only. This procedure is known as dimensional reduction. So, and it dates back before AdS CFT, before string theory. It's a very old idea that has arisen in studies of theories with extended supersymmetry. People realized that the simplest way to write down the Lagrangian of a theory where there are more than one supersymmetry is to start with a simple supersymmetry, but in few dimensions bigger, and then dimensionally reduce. So in a sense, you can think of this as a method to construct supersymmetric Lagrangians. But it's also a useful way to write the Lagrangian and also to understand its symmetries. So for instance, the original symmetry of a theory in 10 dimensions is obviously the Lorentz group in 10-dimensional space, which is SO91. But once we embed the brain inside 10-dimensional space, the symmetry is broken to rotations along the brain, which is SO31, and the group of rotations in perpendicular space, right? So we can rotate these coordinates from 4 to 9. There are 6 of them. And so these rotations form the group SO6. So in the context of supersymmetric gauge theories, this is known as R-symmetry. And it's an important feature of N=4 superrank Mills. So another, yes. Yes, so of course, if you have a plane, like you have a big space, and you have a plane inside it, right? So all rotations along this plane are preserved, and rotations in the space perpendicular to this plane are preserved. But you cannot rotate, you cannot do rotations that rotate the plane itself, right? So, for instance, if I consider the symmetry of this wall, right, it will be rotations, U1 rotations in the plane of the wall. And, well, there is only one perpendicular direction, so there are no other symmetries. Or, actually, this will be Z2 symmetry of reflections. Now, in 10 dimensions, if you embed a 4-dimensional hyperplane, its symmetries are rotations inside, which is SO31, and rotations perpendicular, which is SO6. So this is just geometric symmetries of this setup where you have a plane of dimension 4 embedded in 10-dimensional space. Yes?
In supersymmetry?
Yes, this is, it is precisely the R-symmetry required by supersymmetry.
Okay, okay.
So as we'll see, it rotates supercharges as well, and so it's the usual R-symmetry from superspace definition, if you wish.
Okay, okay.
Of supersymmetries. So since we started talking about supersymmetry, it's clear that we will need to say something about fermions. And fermions living in 10-dimensional space. Yes?
There is something in relation to the word the breaking of the symmetry from SO9,1 to SO3,1 times SO6?
Well, if I write a Lagrangian that describes fields here on the brane, then so the original Lagrangian will be 10-dimensional. It will have this symmetry. But then upon dimensional reduction, I should say that fields are not propagating outside, so the derivatives in the perpendicular direction are set to 0 by hand. Of course, this reduces the symmetry of the Lagrangian, and obviously it reduces it to this subgroup. So fermions, well, there are two ways to define relativistic fermions. One is Dirac fermions, and the other is Majorana. And both have to do with the fact that that you need to define conjugation of a fermion. So Majorana fermions use transposition for conjugation. So the Majorana conjugate spinor is a spinor that is transposed multiplied by charge conjugation matrix. Actually, there should be some other notation for Majorana conjugations, usually also defined by psi bar, but it's not the same psi bar as for the Dirac spinor. So the charge conjugation matrix is, it basically anti-symmetrizes the Dirac matrices. So if we have a set of Dirac matrices and apply conjugation with C, then what we'll get is minus the matrix that's transposed. And then we can write the usual Lagrangian with these Majorana fields. But what we want to do is to also impose the Weyl condition, and that defines Majorana Weyl fermions. So we want to impose the condition that chirality matrix, so this is 10-dimensional chirality. I'll sometimes denote it by gamma 11. It's an analog of gamma 5 in 10 dimensions. So we impose the condition that the fermion has a given chirality. Yes?
It defines uniquely the conjugation matrix, or is that just a property of the conjugation matrix?
Uniquely or not uniquely. It's certainly not completely unique, but yeah, I forgot how it how it goes with uniqueness, but it is essentially unique So well, so I mean, C can be chosen as a symmetric or antisymmetric. That's true, and that is an invariant property. So it is, of course, not completely unique. You can take a similarity transformation on this equation, and then C will change. But some of its properties are basis independent and only depend on the dimension.
Okay, thank you.
So it's like with Dirac matrices themselves, right? So the Dirac matrices themselves are not unique, but they are essentially unique in the sense that their properties necessary for quantum field theory are unique. Now, so this condition, well, in textbooks, mostly people never talk about Majorana-Weyl fermions, and for a good reason, because in 4 dimensions they simply do not exist. And Majorana and Weyl fermions, so fermions can be either Majorana or Weyl. And in fact, Majorana and Weyl fermions is just essentially the same thing. So talking about Majorana-Weyl is a bit of an oxymoron. But in 10 dimensions, both of these conditions can be imposed. And so these 2 conditions are compatible in this sense, and the supersymmetry uses both of them. So let me say a few words why it is not, why these conditions are dependent on dimensionality of space. So you, of course, want to use them in the Dirac Lagrangian. And it is possible to show that the Dirac Lagrangian is only well defined provided that the charge conjugation matrix is antisymmetric, so its own transposition is the same matrix with the minus sign, and also that charge conjugation of the chirality matrix also antisymmetrizes it, as for elementary Dirac matrices. So I leave. It's essentially is a simple question of simple algebra, but I leave checking these 2 statements for you as a home exercise, as a simple part of the home exercise. So, and a complicated part is to show that this condition is true in dimensions. Well, first of all, charge conjugation matrix does not exist in certain number of dimensions, and then it is antisymmetric only in dimensions which are 2, 3, 4, mod 8. In fact, the periodicity, so the Dirac algebra carries a periodicity of dimension 8. So it is essentially repeats itself starting from, so if you start with dimension 2, dimension 4, 5, 6, 7, 10, and then it repeats itself. So this condition is valid in dimension 2 and 6. And you see that in 4 dimensions, one can define Majorana fermions, but you cannot define Majorana-Weil fermions. And it's only possible to define both in dimensions that are in dimensions which are, well, 2, 10, and so on. So in this sense, 2 and 10 are really special for Majorana fermions, so they're compatible with the Weil condition. Yes.
The first property, how does it map to the property of Majorana-Weil?
These are extra conditions. Both of them are extra conditions that are not necessarily valid just from the definition of the charge conjugation matrix.
So these conditions which you wrote down on the right would be like the condition for Majorana-Weil to hold, like the intersection of those two conditions would be the dimensions in which there are Majorana-Weil fermions. Is that the statement?
So,
Okay.
so the logic is, let me repeat the logic. Maybe it was not clear from what I said. So you define Majorana-Weil fermions by these two conditions.
Mm-hmm.
So, and these two conditions are defined as soon as we have a charge conjugation matrix. So but then we need to write a direct Lagrangian.
Mm-hmm.
And the direct Lagrangian only makes sense if the charge conjugation matrix is antisymmetric. Moreover, if we impose in the addition the Weil condition inside the direct Lagrangian, then we need to make sure that the chirality matrix transforms under charge conjugation with the minus sign.
I see.
So checking that this is true is an algebra, and you should be able to do it yourself. So I leave it as an exercise. So the hard part of this exercise is to show that these conditions are indeed satisfied precisely in these dimensions. All right, so, but string theory is lucky to live in 10 dimensions, so where everything works as doctor prescribed, and Majorana fermions exist. So we can write a Lagrangian that contains fermions which are Majorana-Weil. And the simplest one that you can imagine, it contains gauge fields and fermions, turns out to have extra symmetry. So if you write a Lagrangian, which is just this one, so the standard Young-Mills Lagrangian, and then you add Majorana fermions to it, then this Lagrangian will be supersymmetric. Provided that fermions transform in the same representation as the gauge fields, namely that they are in the adjoint of the gauge group. So the claim is that this theory is supersymmetric. One can show that the Lagrangian is invariant under transformations that mix A with psi. and I so let me see. This is not correct. Here is epsilon. And epsilon is also a Majorana Weyl spinor in 10 dimensions. Gamma Mn is, so the direct matrices with many indices are defined such that you take the product of elemental direct matrices and anti-symmetrize. Yes.
Sorry, I have a good question. There are two conditions. The first one you mentioned, you must hold in the Dirac case, but the second one doesn't, right? Like, what's the second one again? Sorry.
Which conditions are you talking about?
C gamma C inverse. No, less more.
These ones?
Yes, that's first one. I'm talking about the second one.
This condition, yes. So this condition is necessary to define Majorana Lagrangian. So Majorana fermions only exist in dimension 2, 3, and 4. Well, actually, they also exist in dimension 5, but with not with the charge conjugation matrix, but with the matrix where has a plus sign here. And sometimes they're called pseudo-Majorana. The second condition is necessary for imposing the Weyl condition inside the Lagrangian. So the Weyl condition will be compatible with the Dirac Lagrangian only if this condition is satisfied.
Okay, so it's like the first one is for Majorana, the second one is for Weyl condition.
Yes.
Okay, perfect. Thank you.
So this Lagrangian is n equal 1 superannuals in 10 dimensions, and n equal 4 is basically the dimensional reduction of that. Yes? Well, you need you were asking about auxiliary fields? Usually you need auxiliary fields to write the Lagrangian in superspace. So I prefer to work in components, and then you don't need auxiliary fields. It's supersymmetric as written. One can show that it's invariant under these transformations. If you apply it to the Lagrangian, simply get 0. So n equal 4 is just the dimensional reduction of this Lagrangian. So you take the fields with 10-dimensional indices and forget about derivatives in the directions that are perpendicular to the brane. Yes? In essentially in the torus, yes. It's basically Kaluza-Klein reduction on torus. Yes, it's n equals 1. So the supercharge here the supercharge has the same indices as epsilon. So it will be a 10-dimensional Majorana Weyl spinor. And obviously it has only a spinor index and no other indices. So it's n equals 1 supersymmetry. So what does dimensional reduction do? Well, let's start with the gauge fields. Then there it is easy. So you need to decompose the indices into perpendicular, perpendicular and parallel to the brane. So you will have the gauge fields that are four-dimensional. And then extra components that have index perpendicular to the brane. So these fields are basically scalars, right? So because they do not transform under rotations inside the brane. So from which we conclude that n equal 4 superangles has, in addition to the gauge fields, it has 6 adjoint scalars. And let me also relabel them. I will assume that the index I runs from 1 to 6. So originally it was from 4 to 9, but just for notational convenience, I assume that it goes from 1. So the Lagrangian then depends on the field strengths, and that decomposes into the 4-dimensional field strengths, the derivative of the scalar field, and simply the commutator between the scalar fields. I don't know if is this obvious to everyone. It's a very, it's in a sense is a simple statement, but it requires a calculation. So I also suggest for you to do it as a home exercise to see how the dimensional reduction works. So then we need to take the square of this to write the Lagrangian. Well, the Lagrangian then becomes this. So we have, now let me introduce also the gauge coupling. So there will be 3 terms coming from fmn squared. One is the usual f mu in 4 dimensions. It comes with the coefficient minus 1. So prefer to normalize everything to 1/2. Then we will have the kinetic term for the scalars and quartic interaction that is of very specific type. Right, so this is just the dimensional reduction of the Yang-Mills Lagrangian in 10 dimensions. So fermions, well, for fermions, let me keep the 10-dimensional notations. And if you do diagrams in n equal 4 superangles, it's always useful to work with 10-dimensional direct matrices, just for technical reasons.
Wouldn't we expect the kinetic term for phi to have the same sign?
You're asking about this sign?
No, the kinetic term.
This one?
Yeah, should be a minus.
It depends on the metric. So I use plus, minus, minus, minus nomenclature. So
Oh, I
the metric for I is actually has a minus sign. And there is a minus for, so in the standard Yang-Mills Lagrangian, there is a minus in front. So this minus times minus for the phi gives plus here.
Okay, I see. It's because if you just like plug these definition from F there naively, you would get the minus. But I think there's something else going on there, I imagine.
But it's also one that is consistent with positivity of the norm for the field, because this is a kinetic term. This is the kinetic term for phi, and it better come with the plus sign. So here I get a plus for a bit of a different reason. So there are two j indices. They don't produce sign, but the commutator. So in the field strength, the commutator comes with an I, and I squared gives plus. Again, this plus is important because so the potential, this is a potential term in the Lagrangian. Potential has to be positive. So the Lagrangian, I remind, is kinetic energy minus potential energy. So this term has to be negative definite. And it is, because a commutator of two Hermitian matrices is anti-Hermitian. So it's I times something that is Hermitian. And if we square, then this I gives the requisite minus. So this Lagrangian is indeed has nice properties of that we expect of well-defined quantum theory. Any other questions? Yes. I don't quite hear the. So the question was about the 10-dimensional spinors, and I'm starting to, I'm coming to that. So yeah, so what happens to spinors? Yes.
I have a naive question. In the beginning, when we talked about dimensional reduction, you said there are these components, and we set the derivatives of components in perpendicular directions to 0.
Yes.
And then here are scalar fields. Initially, we wrote down as the components which are in the perpendicular directions, but
yeah,
the derivatives are still set to be non-zero here.
No, they.
Oh, okay. I see. Okay. Sorry.
So there is no single di derivative here, and that's the essence of the dimensional reduction. Forgetting about part of the derivatives in the fields. Yes. I just wrote it there. So in principle, I should have written it in this Lagrangian as well, but to save space, I didn't. So there is an overall 10-dimensional coupling. But of course, coupling, I mean, dimensional reduction is a trick, and coupling is not particularly, well, I mean, it's, coupling in Yang-Mills theories is always a coefficient in front of the Lagrangian. We can, symmetries are not sensitive to how we write the coupling. But it is true that in this Lagrangian, so if someone gives you this field content, then you would be able to write many interaction terms. So this term is not unique. You can write, well, you can write two independent terms with scalars that would be SO6 invariant. Only this one appears, and there isn't a supersymmetry. So if you add another term, it will break supersymmetry. Also, if we try to make a coupling constant here to be something else, we will not get a supersymmetric Lagrangian. So supersymmetry that we get by dimensional reduction is very rigid. It fixes the Lagrangian completely up to an overall constant that is obviously not, can be anything, cannot be affected by symmetry considerations. Okay, so what about fermions? So to talk about fermions, we first need to talk about the Dirac matrices, and those we need to decompose. You see that they decompose in a transverse and perpendicular directions for the brane. And it suggests to use 10-dimensional, 4-dimensional and 6-dimensional gamma matrices as the basis. But those are the, originally so these matrices form 10-dimensional Clifford algebra, and we need to make sure that that this is respected. So the simplest way to do it, which is again not unique, but it's just simple, is to write them as a tensor product. So then for instance, this ansatz works. So these are 6D Dirac matrices. So it's, you don't need to do any calculations to check, right? Because so what you need to check is that they separately anti-commute on the metric, and in fact, if these are Euclidean, we probably need an I here. So separately, they anti-commute, so because of this tensor product structure, and if you take a product of two matrices of this type, gamma 5 squares to 1, it is necessary to make sure that that the cross anti-commutators are 0, right? So the anti-commutator of this matrix with that matrix is 0 in 10 dimensions, and this here arises in the ansatz because gamma 5 anti-commutes with any gamma mu. So this is one possible way to construct 10-dimensional Dirac matrices once we know Dirac matrices in 4 and 6 dimensions. So from that, we can also find the chirality matrix, which is a product of all 10 Dirac matrices. And it's easy to see that it will be given by 4-dimensional chirality times 6-dimensional chirality. Let me denote it by gamma hat 7. So chirality, in this sense, 10-dimensional chirality is the sum, or better to say, product of 4-dimensional chirality and 6-dimensional chirality. So if you define Majorana-Velley fermion in 10 dimensions, is the same as to say that we define a 4-dimensional fermion with extra indices that transform under 6-dimensional rotations and correlate their chirality. So 4D chirality should be equal to 6-dimensional chirality. So psi, therefore, has components alpha A. So let me use 2-dimensional nomenclature for 4-dimensional spinors. So in this sense, A takes values 1 and 2. So it's a chiral Weyl spinor with 2 components. And then, because of this chirality match, it should be also a chiral spinor of SO6. So A runs from 1 to, can anyone compute? What is the range of A? It should be a chiral spinor in 6 dimensions. How many components will it have? Yes, so it runs from 1 to 4. So let me repeat these calculations. So it's Dirac spinor will have D over 2 components, and then chirality halves the number of components. So if D is 6, this would be 2 to the 3 minus 1, which is 4. And we also will need to add a spinor that will have that will be antichiral. So let me denote it with the psi bar. So it will have indices that are usually denoted by alpha dot, and these are opposite chirality Weyl fermion. So 6-dimensional chirality is such that complex conjugated representation has opposite chirality. So it's usually is denoted by lowering the spinor index. So let's count the number of components is correct. So in 10 dimensions, we have 10 over 2 minus 1, which is equal to 16, 10 to the 4, real components. And real because of the Majorana nature of the fermion. So in Majorana Lagrangian, we only use fields and their transposed, in their transposed components. So we never use complex conjugation. So spinors can be considered real. Let's see how many we get using 4-dimensional notations. So we can just count the number of components here. This will be 2 times 4, and that's 8. But this spinor is complex. We can consider this as a complex conjugate to it. So what we get is 8 complex components. So the counting works, and this is how the spinors look in 4 dimensions. In particular, the supercharges will have the same indices as fermions. So we'll have supercharges which are Weyl spinors with 4 extra indices, and conjugate charges which have the same indices but lowered. And A runs from 1 to 4. So in the supersymmetric language, we will have extended n equals 4 supersymmetry. So the minimal supersymmetry would contain just 1 supercharge, but here we have 4. So what we get is n equal 4 extended supersymmetry. Yes. Can you please repeat?
Yeah, yeah. You're saying you have n equals 4 supersymmetry, so you have only 4 supercharges,
Yes.
but alpha runs from 1 to 2. Why don't you count those?
It's just tradition, so that you count in 4 dimensions. You count minimal number of supersymmetries. So supercharge is a spinor. It always has spinor components.
Okay.
So n equal 1 supersymmetry will have 1 supercharge, which will be a basic Dirac, basic Weyl fermion, Weyl spinor. Yes.
How the R symmetry is realizing this supercharge?
Oh, very simply, because our symmetry is SO6.
Yes.
So indeed, we have SO6 R symmetry. And under SO6, okay, so A mu is a scalar. Phi I is a vector. And it has 6 components. So because of their 10-dimensional provenance. And psi A alpha as well as Q A alpha are Weyl spinors. So it's simply the A is just the spinor index of SO6, so they transform in the spinor representation of the R symmetry.
Ah, okay, okay. Thank you.
And it's simply it's not something that we invent. It comes out of the dimensional reduction. Am I allowed to take a break for 2 minutes, or better not? Yeah, so let's just stretch legs for strictly 2 minutes. So we start 32 past. Okay, so basically in the next lectures, what I will do is perturbation theory in starting from this Lagrangian. Simply computing diagrams, trying to find correlation functions in the expansion of the gauge coupling. That's very sort of mundane task, but it has some nice features, as you will see. Yeah.
Can we obtain this Lagrangian in 10 dimensions from the perspective of strings in 10 dimensions?
Yes, of course. It's you take open strings, and then consider the low energy effective action. That will be this Lagrangian.
Ah, okay, okay. So in 10 dimensions. Thank you.
And this is how it arises in this story. So you take a brain, and there are open strings attached to the brain. Low energy effective theory is, well, basically this, but then you forbid these endpoints to move in the extra dimension, so you get the dimensional reduction. That's sorry? Yes?
In this case, the brain is all the 10-dimensional space.
Yes, yes, yes,
Okay,
yes.
okay.
Yes, exactly. So, so what we get is, well, it's a Lagrangian with some vertices. So there will be, well, okay. So perturbation theory will contain this vertex, this vertex, this vertex. And then there will be a quartic vertex from the commutator term. and the Yukawa interaction for fermions and scalars. So, and then we combine them in all possible ways by the usual rules of perturbation theory. But then there is also a gauge group. All fields are in the adjoint, and I will be interested in the planar large N expansion. So let me say a few words about large N. I'm sure many of you know it, but let me just mention it in passing. So it is convenient to treat separately the gauge indices of so to draw diagrams in two-line notation. So each for each gauge index. So for instance, for the gauge fields, which are matrices with two indices, the propagator in Euclidean space will be this, so it will be 1/8 pi squared, x minus y squared. The gauge coupling squared, then delta mu, and the delta function that describes the contraction of indices, of color indices. So I, j, k, and l run from 1 to n. And we accordingly draw this propagator as two lines connecting. So you see that indices are preserved. So there is always the upper index is contracted with the lower index of the other field. And so we can draw it like that. I contracts with L, J contracts with K. So there is a direction always from upper index to the lower. And the diagrams will preserve this index structure. So for instance, if you have a diagram that, let's consider a simple example. So for instance, if you have a vacuum diagram that contains a gluon loop and the propagator inside, then in the double line notation, this will split into different diagrams because you can connect index loops in different ways. So one obvious way is this. But then there is another way to connect the color indices. So let me try to draw it. It's a bit more challenging to do it. So let's see if I did everything correctly. Right. So I think, yeah, so arrows connections here also work. So let's count what is the prefactor of each diagram. So each of them contains 2 loops. So they will be proportional to G Young-Mills squared, right? Each 1 power of the gauge coupling for a loop. Oh, sorry. I think it's let me just see. So each propagator gives a factor of g squared, and each vertex a factor of 1 of g squared. So we'll have 1, 2, 3 propagators and 2 vertices. So indeed, the factor is g squared. And then each index loop corresponds to contracting to summing over indices. So it gives a factor of n. 1, 2, 3 factors of n. So this will be proportional to g squared times n cubed. Something, yes. So, and that is, if you write it in terms of the 't Hooft coupling and the number of colors, that would be proportional to, or just equal to lambda times n squared. So for this diagram, the counting of the gauge coupling is the same. But then, as you can see, there is only one index loop, right? Yes?
Feynman diagram, there corresponds only one lace diagram like that.
No, there are many.
Oh.
There are many. So you see that traditional Feynman diagram is just the same.
Yes.
It's only the indices that are contracted differently.
Oh, right. Okay. So the
So it's one and the same diagram,
one
one and the same Feynman integral, but different ways to contract indices. So that's the
okay,
point.
That's
So,
what, okay. Thanks.
and also the only thing that differs here is the color factor. So the color factor for this diagram is n cubed, and for this is n. And so this diagram is proportional to lambda without any independence. So in the large n limit, this diagram is suppressed, and this is the leading one. And well, what's the difference between these diagrams? It was a little bit more difficult for me to draw this. And the reason is that you cannot draw it on a blackboard without self-intersection. So these diagrams have different topologies. So this diagram typically is called to have topology of the sphere or of the plane. So if you add the point at infinity, the sphere plane becomes a sphere. So this diagram can be drawn on a sphere without self-intersections. And this diagram can only be drawn on the torus without self-intersections. If you have a good, imaginations, you can even see how torus appears here. But anyway, so the claim is that these diagrams can be only drawn on a torus, and so this diagram in the 't Hooft limit is proportional to n squared, and this diagram is proportional to n to the 0. So in what follows, I will forget these diagrams that are not planar. But in general, if you have a correlation function, then one can use topology to count the dependence on the number of colors. So for that, we also need to classify the operators by the number of gauge theory traces that we can take. And what we consider are single trace operators. So that the operators that can be written as trace of some product of fields. So fields are matrices and adjoint representation, or simply n by n matrices. We can multiply them as matrices, and then take a trace. And so the operators that can be written as that are called single trace ones. So there is a claim that a correlation function of n single trace operator can be written as an expansion in 1 over n where the prefactors are only functions of lambda and of the data sitting in these operators, like their coordinates and so on. And this f of g is the sum of diagrams that can be drawn on a surface with g handles and n holes. So each operator punches a hole in the surface, and each handle adds 1 power 1 over n. So this will be insertions of operator 1, 2, and then up to n. And you can see this happening here. So these are vacuum diagrams. No operators are inserted. So one of them corresponds to g equals 0, so it scales as n squared. And the other is correction for the torus, which is a surface with one handle. So it will be proportional to n to the power 2 minus 2. So it's just scales as n to the 0. Now, I will only concentrate on the leading term of this 1 over n expansion. And you see that it basically, topologically, it's the same as string perturbation theory. So we sum over surfaces of string world sheets with given topology, where the role of the string coupling is played by 1 over n. So in AdS CFT, it's basically the same. It's, the string coupling is not precisely 1 over n, but it's lambda divided by 1 over n. And I think that this correlation between powers of lambda and 1 over n is still a matter of debate, how these powers of lambda that are sitting in these prefactors f of g, how they appear. It's an interesting question that is still being discussed. So what we will see is that when we restrict to the planar theory, some new symmetries that are hidden in the, so that they're not symmetries of the Lagrangian, but they do appear when we restrict the theory to the planar level. Yes?
What was the reason of just restricting to single trace operators?
It's basically this formula, because if you have a double trace, it will basically, well, it's the same as producing two punctures. So you need to count traces to have a well-defined topological expansion.
But so for in the theory, but there are those operators also, right?
Yeah, sure, of course. Yeah, that's true. But so this counting of 1 over n is simple for single trace operators. And one mask, and what if an operator is a single trace plus double trace? So, and this, these things do occur. One has to consider such operators, but we can say that this double trace contribution is a small correction, and it's the small parameter is 1 over n. So if you organize the theory in the 1 over n expansion, then the leading order you can restrict to single traces, and then take double traces
as powers of 1 by n.
Yeah, yes.
Nice.
So another important feature of n equal 4 supermills is conformal symmetry. And I guess you have heard a lot about conformal symmetry in the previous lectures. So the important feature that I will need technical terms is that if you consider a correlator of two operators, then it is only non-zero if they have the same scaling dimension. And in that case, it has a simple power-like behavior with distance, where delta is the scaling dimension of O. In principle, the denominator here can be any constant, but we can remove it by rescaling the operator. So this is writing 1 here as a matter of convention. So you can always rescale operators and get rid of normalization constant. So when people talk about spectrum in conformal theories, they're always talking about operators and their scaling dimensions, because particles do not exist in conformal theories, so it's not a well-defined notion. So the spectrum is just a set of operators and their scaling dimensions. Or a more precise statement is that we want to decompose the Hilbert space of the theory in the representations into the representations of the conformal group. So the conformal group is in 4 dimensions is SO 4,2. And so the operators will be transforming in the multiplets of this group. So this group has rank 3. So any representation is characterized by 3 numbers. And well, these numbers are conventionally chosen to be the spins of the operator. So in 4 dimensions, spin labels form a pair. And the scaling dimension. So the question is how to decompose the space of all operators into the representation of the conformal group that is labeled by the dimension and the spins. Now, spins are half integers, but the dimension it can take continuous values. So it's like with the Lorentz group. If we insist on unitarity, so that the metric here is not uniformly positive. So this group has, so if you insist on unitary representations, they have to be infinite dimensional, and they can be labeled by continuous set of labels. So scaling dimension is not quantized because of the non-compactness of the conformal group. This has an interesting consequence in that the scaling dimensions in general are allowed to depend on continuous parameters of the theory. In this particular case, they can depend on the gauge coupling. So the goal of the next lectures will be, actually of the whole courses, will be on how to compute the scaling dimensions as a function of the gauge coupling. But I guess I'll start talking about it in the next lecture. So thank you very much.
Questions?
Just checking. In the propagator over here, you've put delta mu nu. Is this meant to be the Minkowski metric, or
I'll be.
or
Yeah,
are we
so
Euclidean?
It's Euclidean, so
Okay.
I will write the Lagrangian always in the Minkowski signature, but we'll do perturbation theory in Euclidean.
Fine.
We hope it will not lead to confusion. There's a bit of a subtle point here because fermions cannot be continued to Euclidean at, I mean, it's a subtle point, continuing fermions to Euclidean. For instance, if you start with 10-dimensional fermions, they may run Weyl, and that depends on the signature. So in Euclidean signature, 10 dimensions may run Weyl do not exist. There's another question. Yeah.
So I was a little bit lost with the dimensions. You said there you have the conformal group in 4 dimensions, right?
Yes.
And right now in super young Mills we're talking about 10 dimensions. What happens with the dimensions?
Yeah. So let me repeat again. So we start with 10 dimensions where symmetry is SO91. Then in 4 dimensions we have this symmetry. But then what happens is that in 4 dimensions the gauge coupling is dimensionless, and it is not renormalized. And it turns out that this theory is completely finite. So the coupling doesn't run, there is no beta function, and there is no scale in this theory. So it's scale invariant, and basically scale invariance basically means conformal invariance. So the symmetry is enhanced to the full conformal group, which is SO42 cross SO6. And that's the global symmetry of unequal force apparent Mills. There is also supercharges that extended to a supergroup. I'll talk about that later. But this is how it works.
So again, about the R symmetry, is the R symmetry always the symmetry group of the inner manifold, or the orthogonal direction of the brane?
A good question. So I would make a stronger statement, actually, that any global symmetry in holography is realized geometrically. So you always have some manifold or some geometric feature that realizes global symmetry of the theory. So in that case, this is indeed rotation symmetry of the 5-dimensional sphere. But I guess it's a general feature of holography that.
Okay.
Yeah.
Thank you.
More questions? Well, if not, let's thank Konstantin again. So we'll come back at 2:30, and today